Okay, so for the purposes of trying to get this lesson to Stephanie Hernandez, I'm going to record the lesson that I did yesterday, September 7th, 2017. And I am also going to upload this lesson for everybody in the class so that they can have an opportunity to replay it if they need to. So this section of Unit 1, which is dealing with algebraic reasoning, is going to deal specifically with arithmetic sequences. An arithmetic sequence is a discrete function, and we'll kind of flesh that out later on in the lesson, but not all discrete functions are arithmetic sequences, so we need to make a distinction, but that will come up later. So the other day when we did our math lab, you had to take some blocks, okay, like this, and you put stickers on them, okay? And as you put stickers on the blocks, you needed to determine if I joined together these cubes or these blocks, okay, if I join them together and form a rod, how many stickers do I need for each rod? So in other words, if I only have one cube, I have 6 stickers. If I have 2 cubes, I'm only going to put stickers on the exposed faces of the rod. So I have 10 stickers for this rod that contains 2 cubes, okay? If I add another rod, or another cube to my rod, okay, then I'm going to add 4 more stickers to the entire rod, because when I add this cube, this face of this cube is covered up and this face of this cube is covered up. Okay, if I do it one more time, okay, this one has too many stickers. Okay, 4 cubes in the rod will have 18 stickers. Okay, so I'm going to create an arithmetic sequence that represents rods with stickers on them from 1 to 10. So we said if we only had 1 cube, it would have 6 stickers. If we had 2 cubes, it would have 10 stickers. If we had 3 cubes, 14 stickers. If we had 4 cubes, 18 stickers. If we had 5 cubes, 22 stickers. Okay. If these had stickers on them and we kept adding more cubes, like so, okay, and I went all the way up to 10, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, then I would get 26, then 30, then 34, then 38, then 42, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay. So this is now going to become a sequence of numbers that represents the stickers in the rod, okay? Now, that's easy to do if all I have are 10 cubes to create a rod, because I can just count up the stickers pretty easily. But if I needed to create a rod of 20 cubes or 56 cubes, then this is going to become a little bit more difficult of a process, reiterating each application every time. I could sit here and say, okay, 42 plus 4 plus 4 plus 4 plus 4 plus 4 plus 4, plus 4, plus 4, until I get all the way up to 20, okay? Which 82 would be 20 iterations of adding 4 every time, okay? So when I look at this, I know, okay, I could probably get up to 20, but 56 adding 4 in my calculator or even in my head is going to be a little bit cumbersome. So what I need to do is come up with some kind of general formula so that as I get higher up in the number of terms that are in my sequence, I'm able to calculate it a little bit easier. So I need a general rule. Well, this is my first term, 6. My second term, 2. My third term, 3. Fourth, etc. And as I look at these terms, I know I have to add 4 every time. So I probably could multiply the 2 by 4. I get 8, so I'm 2 off, so I need to add 2. Does that work every time? 3 times 4 is 12, add 2 is 14. 4 times 4 is 16, add 2, that's 18. Yeah, that's going to work every time. So I realize that I have a general formula of multiplying by 4, then add 2. Okay? If I let these numbers be a sub n, in other words, my first term is a sub 1, my second term is a sub 2, my third term is a sub 3, a sub 4, a sub 5, a sub 6, a sub 7, a sub 8, a sub 9, a sub 10. Okay? Then these numbers up here are going to be my n. So now I'm asking, what is a sub 20? A sub 20 is equal to 20 times 4 plus 2, according to my general formula. So that's 82. Now I can do this with ease. A sub 56 is 56 times 4 plus 2. That's 226. Okay? Now I can do this huge numbers down here with even greater ease. Let's find out what is A sub 137. Okay? So I'm going to take 137, multiply it by 4, and add 2. And I get 550. A sub 213 is 213 times 4 plus 2. That's 856. Okay, so we now need, we know what the general rule is. Now we need a general formula, okay? So I already said that we're going to let the place where the numbers fall in the sequence be all the positive natural numbers. And we're going to call them n. Okay? And a sub n is the number of stickers. Okay? So again, a sub n is the number of stickers. Okay? We're going to multiply that by 4. Okay? By n, where n is the number of cubes. And then we have to add 2. Okay, So that's for the number of stickers needed for a rod of any length. Now, how did we get that? And how can I get this if I need a general formula for any sequence, no matter what kind of sequence it is? So this is the general formula for the cube problem, but I need a general formula for every sequence that there is. So how did I get this? Well, I want you to think back to y equals mx plus b, okay? So let's graph this function, okay? It is a function. Like this, okay? Where I'm gonna let one, two, three, 4, 5, 6, 8, 9, 10. Okay, so this is my domain. Okay, and then I need to at least make it up to 42. Let's do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. I missed 42, but that's okay. It'll work out. And this is my range. Okay, so these are my n's, and this is my a sub n. Okay, now let's graph these. Okay, so my first number is 6. My second number is 10. My third number is 14. Then 20, then 18, excuse me, then 22, then 26, then 30, 34, 38, and then 42 is off my graph. Okay. Okay, so what I have here is a discrete function. Okay, so what that means is it's not continuous. Each particular point, okay, each domain and range are particular points, okay, and each point is not connected. So a discrete function is not connected. So all arithmetic sequences are discrete because they don't include all the numbers that are between 0 and 1. They don't include all the numbers between 2 and 3. But you might recall from Algebra 1 and Algebra 2, if I were to connect these numbers, or these points, and reach the y-intercept, okay, and then create this needs to make it to 2, and then create an equation for this yellow line, okay, I would say that the yellow line is y equals mx plus b, where b is the y-intercept and m is the slope. I'm essentially going to create the same kind of general formula but for the arithmetic sequence, but it's only going to include these points, okay? But just to recall, how do I get the y-intercept? It's where it crosses the y-axis when x equals 0. But I don't have when x equals 0. I only have when n equals 1. So in order to figure out what is bumping this up by 2 points, I need to subtract off from the first term the common difference between each term. So the common difference between 6 and 10 is 4. And between 10 and 14 is 4. Okay? So I have 4 each time. But to figure out what is bumping it back up to, I need to subtract 4 from my first number, 6. Okay? So in other words, a general formula would be a sub n is equal to 4 times n, okay, minus 4, right? Because I have to subtract off the 4 and then add the 6. Okay. If I let 4 be my d, then my general formula, so d is equal to the common difference. So this is d. I'm going to replace 4 now with d. So I have a sub n is equal to d times n minus d plus 6. Okay? In order to kind of clean this up a little bit, I'm going to factor out the d. So I have a sub n is equal to d times n minus 1 plus 6. And where 6 is my a sub 1, or my first term. Okay? All right. So in this sequence, remember, every sequence, what it is a list of terms. And we call these terms a sub 1, a sub 2, a sub 3. Okay? That starts with a sub 1, the second term is a sub 2, and so on. The general term is denoted by a sub n. We call it the nth term. So when we write a sequence, a sub 1 is the first term, a sub 2 is the second term, then we say the a sub nth term is anywhere in the sequence, but it keeps going. So every sequence has a first term, but no last term, because it goes on for infinity. Like I mentioned before, it's a discrete function. Okay? This definition can be found on page 611 of your book. And this problem is a discrete function, because when we graph it, it's simply points on a line that are unconnected. Okay, so here's another example of a discrete function. These are unconnected points, right? So for this function, the domain is equal to -2, -1, 0, 1, 2. Okay, it's a set. The range is equal to 0, 1, and 4. Okay, it's a discrete function. If we were to connect these lines, then we would get y is equal to x squared. And it would include all of the numbers in between these points, which is an infinite number of numbers. So discrete functions only include a finite number of numbers. So for the arithmetic sequences, an arithmetic sequence, first of all, is called arithmetic because it's defined by adding a constant value to the previous term. So in the case of the blocks, we're adding 4 to every previous term. Okay, so there's a constant value that's being added, and that's called the common difference. Okay, so in order to get the general formula, you have a sub n is equal to that common difference d times n minus 1 plus the first term. Okay, let's take a look at these sequences down here and determined whether or not they are truly arithmetic. Remember, an arithmetic sequence, means that you're adding a common difference to each of the previous terms in order to get the next term. Okay, so in this case, to go from 5 to -6, we subtract 11. To get to -17, we subtract 11. To get to -28, we subtract 11. So our common difference is -11. And since it's consistent every single time, this is an arithmetic sequence. Okay? To go from -4 to 12, we have to add 16. To go from 12 to 28, we have to add 14. Immediately we realize this is not an arithmetic sequence. To go from 7 to 12, we add 5, but to go from 12 to 16, we add 4. So this is not an arithmetic sequence because it's not a constant value. To go from -6 to 3, we have to add 9. 3 to 12, we add 9. 12 to 21, we add 9. So this is an arithmetic sequence, and our common difference is +9. Okay, so we've found the common difference for each of these sequences that actually are arithmetic sequences. So A has a common difference of -11, and D has a common difference of 9. Okay, so what will the shape of these graphs be, right? So just like in this cube arithmetic sequence, when I graph it, the shape, we don't say that it's a line because they're not connected, but you can still say that the shape is linear. And why is it linear? Okay, the shape is linear because I'm adding a constant number each time. So just like in a line, it's a constant rate of change, okay? So let's graph the first one, okay? So the arithmetic sequence the two arithmetic sequences were A and D, okay? A was 5, -6, -17, -28. So in order to graph this, we're going to need negative numbers. So I'm going to put my x-axis up here and my y-axis over here. Okay, I'm going to graph this, or number this by 5. So 5, -5, -10, -15, -20, -25, -30. The domain will always be the natural numbers. I think I only had 4 numbers, so I went too far. Okay, the first number is 5. The second number is -6. The third number is -17. And the fourth number is -28. So again, you see that you have a linear equation or a linear function. Okay, for D, we're graphing -6, 3, 12, and 21. In order to graph this properly, you need to start down here. And I'm going to just go ahead and contrive this graph the way I want it. So I'm going to start with -6, -3, 3, count off by 6, 6, 9, 12, 15, 18, 21, and 24. So my first term was -6, second term was 3, then 12, then 21. So you can see that the shape of the graph is linear. Let's look at some of these examples. So a gardener buys a plant that's 12 inches in height. And each week after that, the plant grows 10 inches. So 12 inches is going to be my A sub 1. That's my first term. 10 inches is going to be my common difference D. So 12 inches is the height of the plant at the first of the week. Then I add 10 inches for the second week. Then I add 10 inches for the third week, 10 inches for the fourth week, 10 inches for the fifth week. So my sequence is 12, 22, 32, 42, and 52. Let's see how I can plug this into the general formula for arithmetic sequences, which again is A sub n, where A sub n is my output, is equal to D, where D is my common difference, okay? N is my input, minus 1, plus A sub 1, where A sub 1 is my first term. So A sub 1 is equal to 10 times I'm sorry, let's do the general term. 10 times n minus 1 plus 12. So A sub n is equal to 10n minus 10 plus 12, which is equal to 10n plus 2. So with each iteration, I'm going to plug in the n. So A sub 1 is equal to 10 times 1 plus 2, 12. A sub 2, 10 times 2 plus 2, 22. A sub 3, 10 times 3 plus 2, 32. A sub 4, 10 times 4 plus 2, 42. A sub 5, 10 times 5 plus 2, 52. So when I graph this, I'm just going to contrive the graph starting at 12, 22, 32, 42, 52. We have a linear graph. Again, this is our n. This is our A sub n. So the general formula for this growth is A sub n is equal to 10n plus 2. Okay. All right, let's go ahead and do this one example, and then we'll stop there. So for tax purposes, a firm depreciates its $900,000 building over 30 years by a straight line method. Straight line method means arithmetic sequence, because we're going to have a constant common difference. If it depreciates the value of the building by $30,000 each year, let's write a sequence that gives the value of the building at the end of each of the first 5 years. So the end of the first year, it's $900,000. Okay? Then the next year, it goes down $30,000. So $870,000. Then the next year, it goes down to $840,000. Then the next year, $810,000. And then the last year of the fifth year, $780,000. Okay, how did we get this sequence? We simply subtracted $30,000 with each term to get the next term. So in this case, our D is negative. Our common difference is negative $30,000. So our general formula for this sequence is A sub n is equal to negative 30,000 times n minus 1 plus our first term, which is 900,000. Okay. Our next homework assignment is a worksheet. Okay. It will be a review. Let me go get it right fast. It's a little review of our set unit and our set notation. So some of the problems deal with the Venn diagram, which also deals with sets. I lifted this problem and this problem straight from an ACT. Okay, so both of these are reviews. This one's a review of set, and then this one is a review of Algebra 2. I took them from last December's ACT, so if you took last December's ACT, it'll look familiar. And then what you're going to do for each of the successive problems is look for that general formula, okay, that A sub n is equal to D times n minus 1 plus A sub 1, okay? And that's what you're going to look at for each of these problems, numbers 3 to 16. Then the very end also deals with more review and set notation, and the whole thing is due on September 15th. Okay, God bless you.